you very much for your time. What I'm going to do is demonstrate the ICD Stack-Up Planner. And before we begin, I simply would like to show you, give you a general overview of what this tool is all about. This tool is kind of like a Swiss Army knife for those people who are doing layout design. It consists of really two major functions. First and foremost, the Stack-Up Planner, and secondly, this feature called the PDN Planner, or PDN standing for Power Distribution Network. What's interesting about this tool is you may see that these seem somewhat unrelated to each other, but as a matter of fact, what this is trying to do is address impedance issues. In high-speed design, we're going to have impedance issues not only on our traces, but also on our power distribution network as well. And you may say, well, what's a power distribution network? It is simply our power supply and our power planes that are on our boards. And so we want to make sure that we can address and mitigate those impedances, or at least control them, especially if we're doing signal traces. And that's pretty much what we're trying to do over here in the Stack-Up Planner. And we'll talk a little bit about this where I've got my cursor. We are on the cursor here is located in the characteristic impedance column, and then right next to it is the edge coupled differential impedance column as well. On the PDN side of things, and again I'll mention this, that there's another video that goes into great detail. What we're trying to do over here is we're trying to reduce the impedances as much as possible. So if there's any AC noise that is on our power distribution network, no matter what frequency it is, we're able to get it off our power supply and into the ground plane as quickly as possible, so that that noise does not make its way to the components and causes more issues with our signal integrity. But again, covered in another video. Let's jump over here to the Stack-Up Planner. Now you may be saying to yourself, well, any EDA tool out there has obviously a stack-up capability, or you can call it a stack-up planner. But what this one does over here, which other ones kind of fall short of, is first and foremost that they can handle the characteristic impedance equation, so that we know what the rules are going to be when we want to figure out what the trace space and the trace clearance is to get very specific impedances. In addition to that, there's also material information that's provided here as well. And if we want to take a look at the material library, we can simply click on it here, and we can see that there's well over 30,000 materials that are in here. Now, yes, you can go through here and pick and choose things that you think will work best for you here. You always want to have a conversation with your fabricator after you pick them to make sure that, number one, it's not cost prohibitive, number two, that there's no lead time to it, and number three, that it doesn't cause big issues for their processes. Because obviously there's FR4, which has been the standard material for many, many years, but in high-speed design we need something with a better dielectric constant. But usually when we pick other materials with better dielectric constants, there's something we have to sacrifice as a result of that. So we have to be very careful about the ones that we pick. And this tool really is more so that you can have an intelligent conversation with your fabricator at the beginning of the layout. This is not something you want to present to them at the end of the layout and hope that it will work, because you're going to put both yourself and the fabricator at great risk in terms of accomplishing what you're trying to do. But all the materials are here. One of the nice features about this is that if you don't even know what manufacturers are out there, well, it's all listed here. And once you find a material that might be of interest to you, you can always go onto their website and find that material that you have an interest in, find their data sheet there, and of course have a conversation with the fabricator to determine if that material is the best selection for what you're trying to do. Now, by the way, if the fabricator is already going to select all this stuff for you, well, they can provide you this information as well, and it's a matter of you simply looking it up and adding this information into the Stack-Up Planner. If there's a material out there that's not in here, which would be rather surprising given there's over 30,000 materials, but companies do come up with new materials, you can certainly add those materials in here as well. There are certainly sort features in here, so if we right click here, we can sort on based on certain columns. We can also do some filtering as well. Obviously with the number of entries in here, we probably would want to do that type of search. So just letting you know that this library does exist, and it's a good starting point if you are trying to look for materials above and beyond FR4. All right. And then in addition to it, so obviously we have our stack-up over here. Now, impedances are an interesting creature, because impedances are completely reliant upon the board stack-up itself. And as a matter of fact, some people may think that, well, I've still controlled the width of the trace, and I might be able to control the space of the trace on my own. But that's not necessarily true, because if we really think about our stack-up planning, in addition to things like the dielectric constant or the height of the dielectric or even the trace height or the trace width, we know what the impedance is. Okay, and so as a result of that, the one thing that we can readily control outside of the stack up itself is the width itself. So we shouldn't just go in thinking, well, I can create a stack up and I can create separate rules, and that they are disconnected or somehow not associated with each other. And that's not necessarily true. They are very much associated with each other. And that's why these columns up here, like copper thickness, trace clearance, trace width, and so on and so forth, are given to us so that in the end, we can actually come up with not only a stack up that's realistic that we can provide to our fabricators for review, but we can also get characteristic impedances here that we want, and in turn use this information like the trace clearance and the trace width to create our rule set. And so we'll kind of demonstrate that here in just a moment. As you notice over here, there are a number of predefined layers. Feel free to use these. All right. They're viable layers, but if you have a different layer set that you want to do, you can certainly do that as well. As a matter of fact, I'm going to demonstrate that right here and right now. If I wanted to copy this because I want to do something somewhat different, I can do a shift click, and then I can right click here and I can say copy, and if I want I can create a new layer set here. Actually, let's create a brand new one that's completely blank, and then I just simply need to click paste and it'll drop it in. But let's start one from scratch. Let's say, for instance, there's one that's a very different layer stack up here. And yeah, you can move these things by right-clicking and moving and swapping rows and stuff like that. But it becomes a little difficult. And so obviously, and it's not difficult because the tool doesn't make it difficult. It's just difficult because you got to keep track of your pre-preg and your cores and which one's a plane and which one's going to be a signal stack up. So sometimes it's a lot easier here just to start with a clean slate. And that's what we'll do here. So I'm going to right click here and I'm going to rename this stack up to demo. So we'll do that just fine here. And let's begin. So though don't have a lot of time here to really talk about the differences between core and pre-preg and other materials. I guess you're going to get a crash course lesson in the different types here. But if you are interested in more information about this, we at 9.Connects did do a seminar on this, actually a webinar on this back in September of 2015, and it is called the Stack Up, and we did actually use the ICD tool to demonstrate a few things, though there's a number of PowerPoint slides and it goes into a lot more details about the concept of Stack Up. But with that, let's start over here. I'm going to create an 8-layer board. This is a common type of board that we use here at 9.Connects if we were going to do a high-speed design. So let's start off with the very beginning here. I'm going to right click here, and now at this point it doesn't really matter if I insert above or below because there's nothing really to insert above and below. It's the first one here. But what I'm going to insert in here is a core. And a core material is a hardened material. It's a dielectric material, so it's not conductive, and it usually has a copper on the top and on the bottom. Actually, not usually, it always has a copper on the top and a copper on the bottom. And so once they have this material, they'll etch off the copper based off of whatever pattern you have, and depending on what layer it's going to represent on the top and on the bottom. Now, let's put some copper representations over here. So what I'm going to do over here is I'm going to put on a, I'm going to insert above here, I'm going to put on a plane, and actually I'll move this one over here, and I can drag it up very easily. So I'm going to have my plane up here on the top, and then on the bottom I'm going to insert below a signal layer. Now, for our purposes, is there really a difference? The answer is no. Really, just planes are going to have a lot more copper because they're going to represent voltages, whereas signals are going to, obviously, most of the copper is going to be etched off for traces over here. But we now effectively have over here a core material and a representation of two of our materials. Now, what I'm going to do over here is I want another layer above this here. And obviously I'm really not going to put another core here because that's a material all its own, the core with the copper on the top and on the bottom. So I do need to have another dielectric here, so I'm going to insert above, and now I'm going to put a material called pre-preg. And the only difference really between core and pre-preg is that pre-preg is a material that hasn't been hardened yet. It's kind of soft, a little bit mushy, and once you apply heat to it, it actually liquefies, and it now actually becomes a resin or a kind of a type of glue for the simplest of terms here. Right, so now I have my pre-preg, and now I need to get another layer on here. So again, I'm going to do insert above, and I am going to put here a signal layer. And this is actually going to represent my top layer on my board. And then lastly, I need something that is called the solder mask. And the solder mask is really there for no other reason than, number one, cover over the copper traces that are not requiring any type of solder. So when we put solder on our pads, we don't want it to wick down the traces. That's first and foremost, because otherwise we'll lose all our solder. But secondly, we don't want our copper to be exposed to the air, because copper has an amazing way of reacting with the air over time, and obviously it's going to cause some reliability issues. So we want to make sure we do have a solder mask on the top over here. So notice as we're putting these things in, we're starting to see some values here, and we'll talk a little bit more about those as we go along. Now on the bottom side here, I am going to actually put down another pre-preg, okay, because again we're dealing with the core material above it. And then below here I'm going to put down a plane, and then I'm going to put my core material down here as well. So again, we got core material separated by pre-preg, or if it's on the top we can do something called a copper foil. And the copper foil can, once this has been hardened, then they can actually etch off the copper foil. It all depends on how the fabricator is going to do this, and that's why, again, it's really important that you have a conversation with them, because how you get this stack up together is going to be very dependent on their processes. What I'm going to do over here in this last one is I'm going to put a copper here below. It's going to be actually a plain copper. So now I've got half my board done here. All right, and you'll notice that, just as a side note, I've got two planes over here. Now, why would I have two planes here? And then on the bottom here, I would have my pretty much a duplicate of what I've got here on the top. Well, these planes over here are to make sure that whatever activity is going on the top here doesn't bleed down to the bottom in terms of signal integrity issues, and vice versa. We don't want this stuff to start the noise of them to cross over to each other so that they impact each other. So that's why we put these two planes over here. And as a matter of fact, and I'll go into a little bit more detail about this when we talk about the vias, what we want to do here is ultimately keep as much of our traces that has to do with those things on the top between the top layer and layer 3. And yeah, we may have to send traces down below to the bottom, but we want to kind of minimize the amount of traffic that goes between the top and the bottom as much as possible. And we don't necessarily want to have a bunch of different pipes that go, let's say, from 1 to 3 and 3 to 5, or actually it wouldn't be 5, but let's say 3 to 6. Some of them aren't even manufacturable anyways, and some of them are going to lead to signal integrity problems, and we don't necessarily want to go down that particular path. One of the things that this tool is going to allow you to do is to set up stack ups and vias any way you see fit. But again, you got to bring them to the manufacturer, and again, your fabricator, to make sure that what you're putting together is manufacturable. Okay. Now, I'm going to cheat here a little bit, but it's a power of the tool. Obviously, I can continue to draw the same thing down here by right-clicking and inserting below. But what I'm going to do here is I'm actually going to take this one and I'm going to cut it. I could also do an undo as well. And the reason I'm going to do that is I'm going to use a mirror feature here. So I'm going to click on, hold down my Shift key, and I'm going to click on the top and the bottom here so that I can select all of these. I'm going to right click and I'm going to mirror the stack up. And now I have a complete mirror here, and now I have my 8-layer board done. Now, let's talk about the impedances here and what can we do to kind of control those things. Because again, our board stack up totally controls these. Most signals are going to want to have a 50 ohm impedance, and if they are differential pairs, are going to want 100 ohms. Now, if you want something different than that, you can always actually click on this here. So if you wanted to actually try to get some of these to 85, you can set up these things in such a way that you can do it. Obviously, when you do that, you have to be careful, because if you start changing the layer stack up over here in this new pair, it will impact pair 1. But the idea behind this is that you may have different rules where the copper, well, let's say copper trace and the copper width over here could be changed so that you could get different impedances, and then those rules could be applied specifically to those type of traces. But again, if you start changing dielectric constant, the thickness or the copper thickness here, you're going to impact everything. So at least there is the ability to create different rule sets of clearance and width based upon different impedances you may need. For example, USB, I believe, needs 85 ohms, so you could set that as such. But for our demonstration here, let's just assume that we need 50 ohms and 100 ohms here. So let's take a look at the things that we can control here. Obviously, we can change the dielectric constant. Right now, it's defaulting to FR4, which is approximately 4.3. The better or the smaller the dielectric constant, obviously, the better for it. But we can also play with the dielectric thickness as well. And that's where we have usually a lot of opportunity, unless you're dealing with a board that's got some really restrictive height clearances. But generally speaking, we want to get board thicknesses that will work for us. Here's a board thickness of 42. The default one is about 62 mils, which represents about 1/16, which has been the tradition. Does it have to be that thickness? No, it could be thicker, it could be a little thinner. just keep in mind that the board thickness is, number one, there has to be a rigidity to it so it holds the board together. And number two, it also impacts the size of your vias. The thicker the board is, the wider your vias are going to have to be. So if you got a dense board design, yeah, you can go up in thickness, but also you're going to have to increase your via holes in order to allow for plating. All right, so let's play with this over here. We have a characteristic impedance of 64.96. This is a little high. Okay. And by the way, one thing I'll note, you don't necessarily have to have this at 50 ohms. Okay, and 50 ohms dead on the money, because there are manufacturing tolerances. There's humidity in the air, depends on the operator, depends on the calibration of the machine that day. How much time, maybe they waited a second too soon, waited 10 seconds too early, you don't know. So, and plus you're dealing with chemical etchings as well on the copper, so there's a bit of a potluck to it. They're always improving those manufacturing tolerances, but generally speaking, if you try to get this 50.0 on the money or 100.0 on the money, you're kind of wasting your time. So you want to get it in a near ballpark figure, and that's going to be good enough. All right. So what can we change over here? We can change the copper thicknesses. We can change the trace clearances, and as we change them, so for example, the trace clearance, let's just say I want to see what happens when I do a clearance of 8 over here. Well, notice that it didn't change our characteristic impedance for the single, but it certainly had an impact on the edge couple. All right, and this is going up now to 115, where it was originally 105. So maybe I need to want to reduce that. So that's another feature I can do. Now I can kind of play around with these things, but one of the neat features of this tool here, and I'll bring it up here, is this thing called the impedance plots. And the reason why this was brought up is for the very reason that, yeah, we can play some games with this and we can do some guessing to it, but it's really nice to take a look and say, well, based on the information I may have on this particular layer, if I want to try to get this down to 50 ohms, it may behoove me, at least from a trace width point of view, to try to get this to at least 5 mils. And for trace thickness, okay, so this is trace width. For the trace thickness, which is copper height, and this is what I could do as well. So notice the trace thickness, so the copper height isn't going to have much impact on this. So sometimes people want to throw more copper on it, and that's certainly good for thermal purposes, and that's certainly good for power, but that may not necessarily buy you a whole lot in terms of impedance control. There's also trace clearances as well, so you can see how much trace clearance you're going to get as in terms of your impedances. And then also for differential coupling, they put 2 of these on here. So for example, at 8 mils here, I will get an impedance here, the blue trace. Let me pull this out here so you can see a little bit better over here. The trace clearances, okay? So at 8 over here, this is what the trace clearance is going to be. And then here's for the dielectric thickness. So they're trying to show you what's going to happen for both of those factors here, trying to bring them together. So you can certainly use this over here in order to improve the values that you're getting, so you're not totally guessing in the dark. Though, honestly, it's been a good academic investment here to play with these things to see what you get, because then you get a better feel for things. Say, what happens when I make this bigger? What happens when I make this smaller? But that impedance plot certainly helps it along as well. One of the things I have found is certainly the dielectric thickness plays a big role with it. So if I even put this up to 10 over here, you'll see that it definitely plays a big role with this. And you can change these to your heart's content. Now, for the trace, the copper thickness, I am going to make 1.4 because that's 1 ounce of copper. The 0.7 is ½ ounce copper. The interesting thing about copper weight is that it's based off of weight. They call it ounces. And it's based on taking 1 ounce of copper and how much you could spread it, or the thickness that you get if you spread it over 1 square foot of material here. So I believe 1.4 is basically 1 ounce of copper here, and that's fine, and that's pretty typical. You could go with ½ ounce. That's why you saw 0.7 in there. And notice that we got a little bit of an improvement on the edge coupling. Actually, that's really good here because it's as close to 100 as possible. But we also have characteristic impedance issues here that we've got to improve. So what can we do about this? Well, to get this to go down a little bit lower, we can change our trace width, and maybe we can go over here to 6. Okay, and you'll notice that this obviously changed, but we also got a little bit of a drop over here. So we can keep playing with these to some degree until we get this to the desired area that we want it to be. Now also notice here that just because I played with this, none of these are going to change as well, because we're dealing with the difference between microstrip and strip line. This tool has a field solver in it. So as a result, based on all the material information that you provide over here, it can give you very accurate readings as to what each one of these layers is going to do. And that's a good thing, because in most rule sets, you can go in there and you can make those changes accordingly. based on the certain layers. If you're on layer 3, this is the rule. If you're on layer 1, this is going to be the rule. And that's a nice ability to have here. The last thing I want to do here, because I don't want to spend too much of your time on this, and if you're interested in playing with this, let us know. We can get you a demo copy, and you'll probably have this thing mastered in about an hour or two. It's a very easy and intuitive tool to use. The last thing I'll talk about here is the vias. So you'll notice that by default, we always have a through-hole via. In high-speed design, we generally don't want to have vias all over the place. We also have to be very careful about where we put them because we don't want to have manufacturing issues. So what we're going to do is we're going to say, well, you know what, on the top over here, I've got my top signal, and I want to dedicate layer 3 to any signals that I can't fit on the top. But I don't want them to go really beyond the 4th and the 5th layer because I don't want them to really interfere with these things on the bottom. So I want 1 and 3 to work together, and I want 8 and 6 to work together. Okay, so we've already got our through hole, and obviously you need to have a through hole, and it even recognizes that by default. So I am going to enable this, and I'm going to say, hey, start on layer 1, and then I'm going to say stop on layer 3. And then as a result of that, it's already going to give me the finished hole sizes, and I'm going to put this to 8 just to kind of keep it in continuity with it. Now, there's an aspect ratio over here, and this is really simple. There's, as I mentioned before, you have a thickness of the board versus the hole, the diameter of the hole. And as the board gets thicker, in order for it to be drilled and properly plated with copper, you got to have a bigger hole. And most companies can easily do anything that's below a ratio of 8 to 1. Once you get from above 8 to 1, you start thinning out the companies. A lot of companies can still do 12 to 1, but once you start getting up to something like maybe even 50 to 1, which is pretty extreme, you're probably dealing with maybe 1% of the companies out there, and it's going to be a lot of money. Also notice that this declared this to be a blind via, so it recognizes the fact that I'm going from a top layer to some type of mid layer, and that is defined as a blind via. So it has that recognition here as well. Now I could actually also put one between 8 and 6, but instead I'm just going to mirror it here so it knows to put it between 8 and 6 because I'm pretty happy with the way this is set up here. So I'm going to press save, and now I've got this set up here and I'm ready to go. Once I'm done with all of this and I want to get this out to somebody, there's a couple of ways to do this. I can export several ways. Actually, I can use CSV. Obviously, I can do Excel, and I can do this in text. If you have some of these, if you have any one of these tools in here, you should be able to export it out there. And you also, when you purchase this, you just let us know which particular export tool that you need, and that is the one that's going to be activated over here. Also, it can export into the IPC 2581. That's the new specification from IPC specific to fabrication. It's basically a universal one, and a lot of people don't realize this, but both Gerber and ODB++ are actually proprietary formats, though Mentor Graphics and I think UCAMCO are the ones that own those. They generally allowed people to use them without royalties. But the IPC didn't really like the fact that they did have an ownership, so they came up with their own version of it, and it's being widely adopted. And this tool does export stack up information to the standard. So that's the tool here. And again, as I mentioned earlier on, if you're interested in getting a demo of this, feel free to contact us here at 9.Connects, and we'll be more than happy to get you that demo. And again, it's a very simple and intuitive tool to use. You'll probably have yourself wrapped around this and understand what's going on here in probably about an hour or so. Well, thank you very much for your time, and please do look at our PDN Planner video. This video is going to take a look at the PDN Planner of the ICD Stack-Up Planner provided by ICD, which is In-Circuit Design. This product is sold in the United States by 9.Connects. This product is primarily for the purposes of assisting engineers or layout designers in PCB aspects such as the layer stack-ups themselves, and also for the PDN planning of it. Now, the layer stack-up itself is pretty straightforward. It's basically creating the stack-up that's necessary in order to route the board, and in addition to providing the fabricator the necessary layers for them to put the board together. But in addition to that, there is something called the PDN Planner, and this may not necessarily make intuitive sense initially because a lot of people don't deal with PDNs or even know what a PDN is. For the next couple of minutes here, we're going to talk about that, and you can see why this particular tool is a tool that a lot of designers should use when considering high-speed design issues, especially for their power planes. So I do have a quick slide that I'm going to bring up over here, which I think is going to help us along a little bit. So what is the purpose of the PDN planner itself? It's really to address the noise on the power plane. And a lot of times we don't realize that that's a big issue. A lot of times we just throw capacitors at and say, yeah, it's good enough. There's always a general rule of thumb that we should throw at least one bypass capacitor near some type of load. But it goes bigger and deeper than that when it comes to high frequencies and high speed design. Because what are we trying to target when we're trying to get the noise off of our power distribution system, which is basically our power planes? Well, we're basically trying to remove the impedance between the power and the ground. Why is that? Because our environment, whether we're creating that noise or it's coming from an outside environment onto our board, there's noise there, and we got to get that noise off. Well, how do we get the noise off of our DC power supply? Because if there's noise there, it's no longer just DC, it's got AC to it as well. We want to get rid of that AC aspect of it. Well, in order to do that, we generally need to use bypass capacitors. And in order to use those bypass capacitors efficiently, we got to make sure that the impedances between the ground and the power plane, and vice versa, are such that if we do get noise on those, they can pass through very quickly to ground through these bypass capacitors. And it's a lot more than just throwing a lot of capacitors all over the board or just picking a bunch of different values for those capacitors over the board. There needs to be some planning that we have to do with that. So let's take a little closer look at the PDN planner itself. The PDN planner itself has a number of little boxes here, and we'll look at these here in just a moment. But also I want to bring your attention to the plot that we see here. This is impedance versus frequency. The thing you got to understand is that all capacitors have an impedance, and those impedances actually play a role in high-speed design. And we're going to see this here in just a moment, but the idea behind this is that we want to know what the impedances are for a particular capacitance as we move about the frequency. So that's what we're going to do here right now. We're not going to turn on the board aspect of this for now. We're just simply going to take a capacitor from the library of the PDN tool, put it out there, and then we'll take a closer look at it here. So I'm going to right click on this and I'm going to insert below. And when we do this, it's going to bring up the capacitor library. And the capacitor library's got well over 3,000 components in it, and they're all capacitors. Obviously that's what we're going to use for our bypassing. And as we take a look at these over here, there's different ways to sort these and to filter them out so that we can look for very specific ones. For the sake of time here, I'm just simply going to grab one here. Here's this one here, and we're going to insert the capacitor. And by the way, we can add and delete capacitors to this as well. So if there's a capacitor that somehow is missing from this, though unlikely, but if there is one missing, you could certainly add it in there as well. So we're going to insert this capacitor, and we're going to bring it up, and now we're going to see our results of this particular capacitor. And let's take a closer look. As we're talking about impedances here. And again, we want to get these impedances as low as possible. We're going to see that this is our target impedance, and we'll see in a moment where this comes from. But for now, let's just look at our capacitance. As the frequency gets higher and higher, you'll see that the impedance continues to go down. All right, and it will come down to the point over here, which is called the resonant frequency. And the only reason it won't go all the way down to 0 is due to the fact that it has what's called an ESR, or equivalent series resistance, which is basically the resistance of the material. All materials have a type of resistance to it. But instead of it also going down any further, it starts to go up. And this is the inductive effects of the capacitor. And it seems weird because a capacitor is an E-field type of creature. It's supposed to deal with E-fields, but what we find is that in the model for the capacitor in higher frequencies, there is what's called the equivalent series inductor. And the equivalent series inductor starts to play a big role in this in the higher frequencies. Okay? Now the capacitor that we picked over here is pretty small, and the smaller the capacity, the capacitor, the higher the frequency it can handle over here. So if we picked another one with a larger value here, we'd probably see it further down here. And we'll see that in some examples we bring up here in just a moment. So with this, we can get an idea of where we stand if we just put, let's say, one of these onto our board. Well, what if we decide, for example, that we're going to put 10 of these on our board? Well, we can put 10 in there, and we can update it, and now we can see that if we put 10 of these on our board here, we certainly get a better result here, and it's now bringing us over to our target line, and even at a certain frequency here, we're below the target line, which is even better. Okay. But what I want to show over here and emphasize is that, look, we put 10 of these things on here. Well, what if we put something like 100 of these? Maybe we have a big board. Is 100 of these things going to solve our problems? Not really. We've got other frequency issues over here that we've got to deal with as well. So one of the things we've got to keep in mind when we're doing this is that throwing the same value of bypass capacitor onto the board isn't going to solve all of our issues. Now, it might make our lives easier when it comes to bill of materials, but we've got to start thinking of other capacitor values too, so that we can get all of this line as close as possible to our targeted frequency. So what I'm going to do in this tool over here, because we could save these off, is I created a scenario where we have a bunch of different capacitors, and let's take a look at those. So let's do an open, and we're going to bring up this one where the caps commit to 100 picofarads in steps of 10x. All right, now let's take a look at this over here. So we have a bunch of these on here. So we have C1 through C7. We're not going to turn on C8 for now. They are quantity 1, and you will also notice that these are pretty much going in increments of 10x, so with the exception of one because I didn't find it here in the list, so that's why we see a little bit of a gap here. But here's the highest frequency. Here's the second highest frequency, the lower frequency over here as we go to C2. As we go to C3, we're seeing that one represent the lower frequency, yet a lower frequency. And as we go all the way down to C4 to C7, we see them incrementally dropping. So it's kind of a neat effect over here. Now, generally speaking, when we put the capacitors together, what we're trying to do is we are trying to ride their resonant frequencies. As I mentioned earlier on, the resonant frequency is the lowest point of the impedance. And what's kind of neat about this is that when we do throw all of these capacitors on here, well, what are we really creating on the board? We are creating parallel capacitors because all the capacitors are all going to the same power plane and they're all going to the same ground plane. And so that allows us to kind of ride the lowest impedances of each one of these capacitors. And as a matter of fact, you see this on the lower frequencies. So here's C7, and as C7 is starting to go up, the impedance of the next frequency is starting to pull in, and because it's available here, then the overall result, and that's what this red line is over here, is it's riding the next lower frequency. Same thing for C5 here as well. So what we're trying to do is take advantage again of all these parallel capacitors, because if you think about it, putting aside the capacitance aspect of it, all these capacitors have a effective series resistance. Okay? And because they have that, these resistors, these ESRs, are all in parallel with each other. And the general rule of thumb with those things being in parallel with each other is simply this: the smaller value wins out. If you put a 1 mega ohm resistor in parallel with a 1 ohm resistor, the answer is pretty much going to be a 1 ohm resistor. And that's what we're doing over here. We're taking advantage of the fact that by putting these on here, these ESRs, we're basically riding along this, and by putting different values in there, we can try to keep this below this particular line over here. Now we're seeing another effect that's kind of happening here, and it starts to happen in the higher frequencies once you start to get beyond 10 megahertz, and especially beyond 100 megahertz, and you're seeing what's called an anti-resonant peak frequency. As a matter of fact, you already see it over here where it should have turned down here, but it spiked up and now it's going down. And this is kind of counter what we just said before. In the past, we don't just want to use all of the same capacitors, but we also have to be very careful about just sprinkling different capacitors around the board, because what we may do is create so many of these anti-resonant peaks, we're actually undoing what we were trying to do to begin with. And all we're doing is just adding capacitors, which is just more money from a bill of materials perspective, and that's not the point of doing this. So what can we do about these kind of things? Well, there's really two things we can do. The first one is we can certainly add more capacitors to it. So right now our quantities here are at 1, but let's say we add 10 to these, right? I'm just putting these here just to give a demonstration. So here's C1, and it certainly helps C1. In fact, it brought it down way below this line here, but you can also see that there's another anti-resonant peak that showed up because of it. What about C2? Let's see if we can do something with C2. So let's throw in 10 over here. So again, we're doing this, but again, we're getting these points. So more than likely what we need to do is bring in some capacitors of other values. But hopefully you're seeing the value of what this tool is providing, because if I just pick these things blindly, threw them on the board and manufactured it, that's an expensive way to determine whether or not I got the proper impedances handled, depending on the frequencies that we see over here. Let's turn on C8 here for a moment. So this one is 3.3. This one goes a little bit between C2 and C3 over here. So we're going to turn this one on. And after we turn this on, we do get a little bit of improvement, but again, we still have a spike here. So maybe adding a few more of these might help it, maybe not. But again, that's what the power of this tool is over here, is that you can determine based on the number of these and the different values of these, you start getting a better feel for getting it as close as possible to this line here. Now, let's bring in the power plane, or pardon me, the entire board itself, not just the power plane, the entire board itself. And that's why the PDN Planner is generally brought in with the stack-up planner. You can purchase these things separately, but you really want to have the stack-up planner, because if you've done all of this work over here and you truly know your stack-up, then the PDN Planner is going to be far more accurate. Now, you can define these without the stack-up planner, but I do want to use the stack-up planner because, again, I want to use the power of what the stack-up planner provides, and I'm going to use one of its default stack-ups. So I'm going to use the 8 layers default stack-up at this point. And of course, if you have a specific layer that you have, you'd see that in your list as well. If I don't have it, I can certainly define those. Then the plane size here, we'll leave this here for now, but basically, what's the size of your board? All right. And then from there, we need to talk about the VRM. So we got to set up one more thing here in the VRM. The VRM is the voltage regulator module. It's a nice way of saying the power supply. And this one's actually really, really important because, believe it or not, your power supply can handle a lot of the low frequency ripples and other AC noises on your system, generally up to about 1 megahertz. Okay, so what do we have over here? We have certain things that we want to tell it. Are we using switching mode or are we using linear? We also have over here the voltage that we're going to operate at. So 3 volts is 5 volts. We want to put 5 volts in. Our current, our max current that we think the board is going to need to do this, to operate properly. We also have what's called the current transient percentage. At what's the percentage of time that the current's going to be somehow in motion? All right, and the default is 50%. So don't look at it as really a duty cycle per se, because it's not a voltage, it's current. It's what percentage of time is that current going to be constantly in motion? And obviously, if you're doing a digital design, it's always going to be 50% of the time, because every time you swing that thing, swing the rising edge up or down, it's going to have an impact on it. There's also ripple as well here. So how much ripple do we expect to be on the power supply? Now, you can build a very, very clean power supply, but we got to keep in mind that the outside environmental factors will play a role in this here. So just because you have clean power doesn't mean that the power is going to be clean once it gets to the load. There can be signals that are coming on from outside environments that are going to disrupt that power supply close to the load. So we should account for some type of ripple into this. All right. So let's turn on these things and see what we get. At least let me turn on the ZVRM, because over here it is represented. And if we turn this on, do notice that it's going to bring some improvement over here to a portion of our frequency and our impedance. So if we go here to ZVRM, I'm going to turn this on, I'll hit return, and now we've got quite the improvement. Again, it doesn't matter if this is choppy. I know we all love our straight lines. The intent of this is not to have a straight line. The intent of this is to keep it as close or below the target line as much as possible. Okay, so we cleaned up this area very nicely and very quickly, because our VRM, our voltage regulation module handled that just fine. Now, obviously, we've got some other things going on over here. And what's interesting about high-speed designs, believe it or not, our board itself can be of great benefit to us. So where bypass capacitors tend to kind of peter out in terms of their ability to handle high frequencies, our board actually kind of jumps in and gives us a hand with that. Okay, so in order to turn that on, we got a little more information. By the way, our target frequency here is strictly based off of what we got for our VRM. All right. And from there, we've got our F-min and our F-max. And these are really just kind of, where do you want to start this graph and where do you want to end this graph? And for now, we'll just leave those alone. The key one is our target frequency, because we want to see that, hey, if we're going to run a 200 megahertz clock, is our impedance okay or not? So in fact, as a matter of fact, we already see that line. It's the black line over here. And right now, this isn't looking very good at all. We're at 10 ohms impedance. This would be very, very problematic for this particular board. So obviously, you'd want to see if we can remedy this a little bit. The first thing we can do here, just as a side note, is let me throw a few more of these in here and see if we can do it. That actually helped it out tremendously, okay, by putting those in there. So we can put a few more into these, but remember, these are going to represent the lower frequencies, and so they won't have as much of a dramatic impact on the higher frequencies. These would probably require some either more or additional capacitive values that would impact this here. But this looks pretty good now just by adding a few more of these capacitors. And obviously if you have real estate issues, throwing these down kind of willy-nilly could be an issue as well. All right, let's turn on what the plane effect is going to be. So let's turn on the plane over here. I am going to turn off the via loop inductance for a moment. I'll talk about that one here in a moment, but let's turn that one off for now, and let's go ahead and turn on our plane. Okay. Now, wow, kind of maybe look a little messy to you. And because the plane here is of a certain color red and our overall result is of a color red, it may look a little confusing to you, but at the end of the day, what we're most interested in is this deep red color here, and this is actually looking pretty good. So it didn't have a huge impact on it. We're still near our line, but we still possibly have some issues over here. Now you may say, look, this is at 200 megahertz, or at least our target was 200 megahertz, and this is looking great. So do I really care about these other ones up here? And the answer is yes, we do, because unfortunately there's this fickle thing called harmonics, and we got to make sure that the harmonics are not going to cause any problems as well. So I'm going to kind of zoom this in over here, and what we're going to do is we're going to change this from 0.01 to, let's say, 50 mega ohms. Okay, and we'll press our tab key over here and take a better look at what's going on. So again, the bright red area here is what we're concerned about. And obviously at our target frequency, things are looking good. At our third harmonic over here, which is this dotted red line, things are looking okay. And for our fifth harmonic, not so good. We definitely would want to try to find capacitors in this area that would help improve and bring this thing down below. Do you want this? You know, you may say to yourself, is 1 ohm okay? Is 10 ohm okay? Look, the whole reason for doing this up here is to try to get it as close to this line as possible. And if it's starting to rise quite a bit above this line here, you're putting yourself in danger of having noise that you're really not going to be able to handle unless you start popping capacitors off the board by reworking them and putting them and putting on other values. And that just becomes a really difficult endeavor. It's much easier to use a tool of this nature. So let's look at the seventh harmonic here. Seventh harmonic isn't looking as bad here as well. So far so good. So with a little more effort here and trying to figure out quantities and values, we could probably get this all the way down. Now, two other things to mention over here which we're capable of doing. One of them is the via loop inductance. And I'm going to bring up a slide over here to explain what that is. So give me a moment here to put that in here. So the via loop inductance is the result of us putting down capacitors along with vias. We're going to probably use surface mount capacitors, right? They're the smallest ones for our board real estate, but we're going to have to put some vias, one to the power plane and one to the ground plane. But that area where we put the vias along with the height is going to actually create a loop inductance area, and that's not a good thing. So, for example, one of the not so better ways to do this is putting these things end to end, because we can actually increase the loop inductance area. A slightly better way to do it is to put it side to side, and to even cut the loop inductance area even further, we can put them D side. And though this one is one that was specially made, it actually has two vias and pad. And of course, if you're doing vias and pad for a BGA, you may as well do vias and pad for your bypass capacitors as well. But this was a special case for an RF one where they put two sets of these in here and they really concentrated that field so that it wouldn't have an impact on everything else. That's a little bit extreme, but these three are the ones that are provided in the tool over here. But hopefully you get the idea that you want to keep these things as tight as possible. Can you always do this? The answer is probably no. You've got board real estate issues and you may have to go end to end, but a lot of times going side to side is a lot more efficient. Now, with that being said, we've got some options here. The via loop inductance itself, we need to know the package and we need to know the side that it's on. So let's turn this one on and see what we get. Okay, so when we turn this on, we do see some shifting going on, and we still have some issues. So what was not really a problem before in the third harmonic has now kind of become a problem. All right, now we can also turn on the via spreading as well, and it also depends on how we set up the via spreading. So let's move this over a click, and you can see these are all set up to be end. We'll turn this on first so we can see the result of it, but we can always play with the fan out here to determine what would be the best way to handle these things. So we do get a change here. Okay, we still got our bumps here, and we can start again playing with this aspect, saying, okay, as long as I keep these things maybe on the side, for example, all right, that helped out a little bit. So this smoothed out here. Maybe it might help out here a little bit as well. So there's a little bit of play that needs to be done with all these values. Here's a situation putting them side to side didn't actually help. It actually made the situation worse. So hopefully you can see the power of this particular tool here, that this tool is here to help and assist you find which capacitors you want to use and how many of those capacitors, so that you can get all of your impedances for your power distribution network as close to, if not below, this particular line. And just to show you just a final example here, let me do a file open. This was done by the creator, Barry Only, and we'll bring it up over here, and you can see that he's actually put together, this is based on 37 different capacitors. Well, there's 8 different capacitors, 9 different capacitors, but a total of 37 different capacitors, and you can see he got this down rather nicely. So, well, if you have any other questions with this, feel free to contact us here at 9 Dot Connects, and we'll be more than happy to address those questions for you. Thank you very much for your time.